So I am in the Math for Experimental Data Analysis group. So today I'm going to talk about interaction energy optimization problems related to computational chemistry, mathematical biology, and signal processing, specifically some communication problems. So currently, the work that I'm mostly going to talk about is previous work before I began here at LBL. I just started in the last month. So currently I'm working on Gaussian process regression problems, and we're interested specifically in like using computational tools to approach classical regression problems, but also dimension reduction and manifold learning using Gaussian processes. My mentors are Jeffrey Donatelli and Marcus Novak, who are both in the audience. And here you see a few relevant equations and some images which correspond to Gaussian processes. Okay, so jumping right into interaction energy optimization. The situation here corresponds, basically you have like identical point masses or charged particles, identical particles, and you have like a force between these particles that depends only on the distance between points. So like a physically realistic model, you can think of like electrostatic, charges like electrons interacting. A physically realistic model often has like this sort of strongly repulsive force in the short range to avoid collisions between particles. And then in this specific case, you have like a attractive force sort of in the long range. And if you look at like just two particles and you optimize here, you have sort of a sweet spot where the energy is minimized amongst those two. And that's simple. But then once you start to add a lot of points in space, the dynamics for these, particle simulations get really complicated. So self-organization is kind of an interesting phenomena that happens for materials. You can have sort of, if you look at these particle interactions, you can find tetrahedral or icosahedral symmetry naturally in various domains. And it's really sort of an unsolved problem. It's an interesting scientific problem. For these sort of more realistic models where you have, maybe non-radial potentials and many different types of particles, you think like typical molecular interactions, things are a lot more complicated than the model that I'm talking about here. But I think the main takeaway here is that like this simple model is already really complicated, and we can learn some things about how this self-organization sort of happens by investigating this simpler model. Okay, so one of the large problems with these particle interaction problems is that there's a lot of local optima. There's a lot of spurious local optima. And for some of these problems, if you look at like, say, electrons, and you want to optimize energy on like electrons on a sphere, constrained on a sphere, there's conjecture to be like exponentially many local optima just in the number of points that you optimize over. These images here, these are 2-parameter problems. These are just some test functions, but the main idea here is you've got like already for 2 dimensions, there's a lot of complicated things that can happen when you look at a non-convex optimization landscape. And the situation that I'll be talking about, you have even more parameters, and the problem's highly non-convex. One thing I want to mention here is there's a lot of really interesting problems in applied mathematics that have very non-convex landscapes. So for example, if you look at neural network optimization, which is driving like machine learning and deep learning success in various engineering realms, the optimization landscape there is very non-convex. And so that's one thing shared for these particle interaction problems. Another thing that's sort of shared actually between neural networks or deep learning optimization and these particle interactions is they're highly parallelizable. So GPUs have improved the performance for deep learning applications, and we have a lot of great sort of hardware for optimization of neural networks. A lot of that carries over actually to particle interactions as well. Okay, so For the rest of the talk, I'm going to focus on a very specific energy optimization problem, which corresponds to optimizing points on a sphere. And I'll talk a little bit about why these are interesting configurations to look at. So you have a few examples here. Basically, the main idea is that these have applications in signal transmission. So if you have these well-spread point sets, which you can obtain by minimizing energy, then you can use these for they have nice statistical properties. So if you look at these two sort of images on the left and right side, there's a pentagonal sort of motif here on the right, which is embedded sort of on the one on the left. These are two different optimization problems, but the idea here, you can't see it that well because you can't see the backside of these things, but these are actually obtained by optimizing antipodal points. It's basically optimizing lines for best sort of spread. So these are packing problems. These, in the context of like signal transmission, these take the name of like error correcting codes, and these were used, I think, in the 70s for the Voyager space mission for data handling. Okay, so to go into more detail about like how are these used for signal transmission, what you can think of, the sort of general situation you can think of is like, let's say you have like you have radio data you want to transmit, and there's physical conditions in the medium, say there's like trees or buildings or something that make it so that certain transmission scheme is going to be better than another. And this is sort of captured in this channel vector H here. And okay, so how do you use these well-distributed point sets to send a message? You basically choose one of these which is most aligned with the channel vector, and you get like maximum signal to noise ratio. So there's a whole literature on multiple input, multiple output antenna design models, which makes use of these antenna packings, these particle sort of spread on the sphere. This image here kind of gives an idea, but you don't have to have multiple antennas. The point of these multiple antennas is for more sort of data uplink. You have more data capacity in your channel. So this idea of having a code book and using it for data transmission, the main idea really just comes down to rounding once you've already generated your code book. So you have some channel vector, you measure it. This is just, again, physical conditions, say in like radio signal. You pick some code book and you round it to the closest, like you take your channel vector and you round it to the closest element in your code book. And I guess this red dot doesn't show up here on this for whatever reason. But there was a red dot here. But the main idea is this blue dot in this grid here. The quantization or the rounding just sort of takes it and pushes it to the closest grid point. And that's the same thing that's basically happening for these signal transmission problems. Once you have a packing, you round. Okay, so we developed a method basically to generate these packings, which can then be used for the signal transmission problem. And there's two main ingredients of this optimization method. The first one is the second order method. It's a trust region conjugate gradient method we use as our optimizer. And the second aspect is we do some kind of random sampling on the sphere, on this manifold. So if you haven't heard of trust region conjugate gradient method, it's basically you compute the Hessian for some region, and then you use that Hessian to give yourself sort of a second order sort of approximation to the optimization landscape in a neighborhood, and then you compute that only so often to save time, because it's computationally expensive to compute the Hessian. So you compute that only when you're sort of outside the region where that approximation is good. The random sampling is important here because you need to have a lot of sort of different initializations to handle this problem of the spurious local optima. So our method, we call it basically trust region conjugate gradient, trust region. Let me try this. Trust region stochastic tuning for matrix incoherence. It's trust MI. What we find with it is that it performs well compared to competing methods for generating these packings. And the plot you see here sort of shows that visually. So there's a known optima sort of packing quality, which is measured by this coherence. So the lower the coherence is, the better the packing is. Neither of these, this alternating projection or this trust MI region, neither of them attain the known optima, but the trust MI region, trust MI method is sort of better for quality. So the last thing I'll mention is that we parallelize this just natively. We use PyTorch, and it led to about 3 times performance and time spent when moving from just a consumer CPU to 6-core CPU or a GPU. This was like an A100 GPU that we used. I think I've reached the end of my talk. Thanks for listening, and special thank you to my collaborators.
Thanks, Josiah. Any questions? Yes.
How do you balance the work of the trust region from the random sampling? Is there some ratio of how often you randomly sample?
Yeah, it's just experimental. Okay, depending, I think the big thing is the size of the problem. Like you have to sample more, and it seems to be that it's probably like what we do is just we do something like quadratic or polynomial, and the size of the problem, that's how many samples we take. But it might be exponential if the problem gets really, really big.
But you fix the amount of sampling you do. You don't vary it in the course of the optimization.
Yeah.
Thanks.
Thank you. Before the next question, Justin, would you like to come up and start switching slides? Are there any other questions for Josiah? Yes.
So Josiah, I guess I was curious if there are other examples of cases where this would be helpful besides radio transmission.
I think in general, like the ideas carry over to like any kind of interaction energy. So I think these are interesting, like particle physics, I guess. Modeling molecular kind of interactions. Yeah.
We have a question from Zoom.
Felix Wader, and he or she asked, what's the benefit of random sampling compared to sampling on a grid?
So the big problem is we're on manifold, like we're actually on it like a sphere, and so you don't have like a natural way to sample on the sphere, and that's part of like you're trying to get well spread points on a sphere. And so that's kind of the end goal. So if we had it to start, we'd be done.
Okay, thank you. Let's thank our speaker again. Thanks, Josiah.